All right. Thank you, Mani. So as Mani said, I'll be talking about some of the work that has been done recently by Pranav Puthan, my former PhD student. He just graduated earlier this year, and with Pranav and with Gino. So I thank the organizers for this opportunity to give this talk. Fond memories of visiting ICTS a few years ago when there was another workshop, and I do hope to connect with you all again in person soon. So this work is funded by NSF and by ONR. So let's take a look at geophysical wakes in here. And geophysical, can you see my cursor?
Yes, yes.
Okay, perfect. So here on the left, there is this picture of an atmospheric mountain wake here. So this is there are mountains coming off the various islands, and then you see the carbon vortex street in here. These are island wakes in here. And then here, this I thought was an interesting picture where you see measurements of a wake of a headland. And here what you see is this dipole eddy that has formed. And this is a tidally modulated wake. So also, if we now go to the Abyssal Ocean, so oftentimes we have 3D topography, or perhaps a smaller scale than the big 2D feature. For example, this is Luzon Strait, and then Luzon Strait, where we did some simulations for some time a few years ago, and Luzon Strait is basically like it's a double ridge system on the large scale. But it's not only steep, but highly corrugated. So if you look at, for example, this particular patch in here, then you have these sort of gaps where you have strong tides roll in and out. And so, for example, here so this is actually taken from Pinkel et al. 2012, where they were looking at breaking topographic waves. But as part of that, Martin Buseman did some simulations. He was using a very coarse resolution MIT GCM there, and you can see that there are these associated with the strong currents. If you look at the vorticity in here, you've got these vertical wakes that are spun off the sides of the flanks of the topography in the islands. And then so that was the deep ocean, and here's the coastal ocean. So this is a lot of work has been done by investigators at UW on the wakes at 3 point TTP. And here you're seeing an example where you have the flood tide in here, and then 2 hours after the flood tide, and you see this. So these are drifter tracks, and you see these drifters sort of roll up into this vortex, and this flow separates off the tip of the headland in here, and you see the vortex in here. And then here's another example, which is taken from a paper by Jen Manikandan and others. So this was work done as part of the FLEET experiment sponsored by ONR. And in here also, so these are this is Palau, and you see these wake-like structures in here. Now here, okay, I'll talk about that later. So this particular conference, the title has internal waves in it. So I thought that let me start by a short contrast between 3D and 2D topography. So these are internal. This is a schematic of internal tides from 2D topography. So in the spanwise direction into the plane of the computer here, it's uniform, so it's 2D topography. And then if you have a pure tide, so no mean current going back and forth, then you launch internal gravity waves. And so some characteristic parameters that come into that problem, and we'll see that again in the 3D problem, is so this is the excursion length. So it's u0 by omega is the excursion length on one side of the mean position. And then if it's strongly stratified, as it usually is, then that length has to be compared with sort of an inner length scale, because really, if it's strongly stratified, there is a flow blocking, and it's only the upper region of the ridge, which is, let's say, has a vertical extent of u0 by n, which is an active radiator. And then, of course, you have the slope angle, and depending on whether it's critical. So critical is when the slope angle beta is equal to that of the phase line. So that's when you can get strong nonlinear effects and turbulence right at the slope itself. And depending on what the situation here, you can get breaking internal gravity waves. Now, in the 3D case, of course, fluid can flow around the obstacle to generate wake eddies. And for that, you have a schematic in here that's borrowed from McCabe et al. 2006. And you can see the slope down here. And of course, there's a slope like so, and there's also a slope going like in the orthogonal direction. And so these are the isopycnals. So the isopycnals going up and down, those are associated with the launching of internal gravity waves. But at the same time, the flow can go if there's a current, or if the tidal excursion, this 2u0 by omega is the tidal excursion, is sufficiently large, then the flow, as it's oscillating back and forth, can generate a wake as well. And what we know about at least internal tides is that the 2D case has more efficient radiation than 3D. So that has been shown in the past. So this is a simulation of internal tides, and this is taken from a paper by Jalali and myself, Masood Jalali. And so here what we are plotting is, so what we have done is that we have taken a box of Luzon Strait, and we have scaled it down in terms of the length scales and so on, keeping all non-dimensional parameters the same, except the Reynolds number. But the Reynolds number is large enough to get turbulence. And in here you can see that there's a lot of mixing associated with this, and this is a 2D topography, but it's a 3D large eddy simulation. You can see this internal wave energy radiating out as beams and then hitting the surface kilometers away. Yeah. So, and then this picture in here is showing the criticality of the slope. One means that it is critical, supercritical, and subcritical. And so it's pretty steep topography, and you get strong turbulence at the flanks in addition to the turbulence associated with the beams. So now let's move to wakes. So this is an example of a wake, checking the timing, yeah. So wake vortices. So these are wake vortices in the lee of a small island. So it's a green island, really small. It's like 7 kilometers down here. And so if you look at the pattern shown in here, then you see this sort of a sinuous kind of wake in here. And that the authors sort of try to sort of say that, hey, I mean, if you look at cylinder wakes, they look kind of similar in here. So this Reynolds number 150, Reynolds number of 5,000. And now, since the island is pretty small, so these are wakes at pretty high Rossby numbers. This is the regime that we will be exploring in this talk. Now, there are tides. You can't get away from tides in the ocean, so it's not just a steady current. And so by the way, the steady current here is the Coriolis. And so let's talk about the tidal signal in the wake. Is there a tidal signal? And in these observations, what they find is the following. So this is the past spectral density of at two different probes. So this is W1 and this is W2. So they're in the near wake. And with W2 being closer to the island compared to W1, Green Island. And then here you can see, of course, a broadband. So these are turbulent wakes, but also you can see M2, A1, and M4 very, very clearly in the wake in here. And the authors say that, hey, we don't see the natural shedding frequency. We'll talk more about that. That is determined by the flow velocity and a characteristic lateral length scale of the object, in this case, an island. So what was our motivation in here? So our motivation is essentially to see how do tides affect this. We know that if there's a current flowing past an obstacle, I mean, there's going to be a wake. So now you have a tide. And if there's strong tidal modulation, then how does it affect the flow separation, the vortex dynamics, form drag, and also where does the turbulent dissipation occur? Are there hotspots of turbulent dissipation? And for doing this, we will do turbulence resolving simulation. At least the energetic scales of turbulence will be resolved using an large eddy simulation model. And we are motivated to do these simulations because pretty much all the prior simulations have been either hydrostatic, and as far as I know, none of them have taken account of the tide in terms of wake dynamics. So to do so, we constructed this model problem in here. So this model problem in here, you have a current, and superposed on that, you have this tide with an oscillatory frequency, f sub t. And there are many dimensional parameters associated with this problem. So you have the buoyancy frequency, and so there's it's an underwater submerged topographic element. You have, of course, F, the Coriolis frequency, you have the tidal frequency, you have the current, the mean current, U sub C, then you have the tidal oscillation amplitude and velocity, U sub T, and then you have the height of the topography, D is like the base diameter, and of course you have the kinematic viscosity. So the regime that I'll talk about today is that of relatively weak rotation. So the Rossby number is greater than order 1. So we include rotation, but Rossby number is greater than order 1, and a strong stratification. So the Froude number based on the current velocity is, sorry, there's a typo here. The Froude number is less than order 1, much less than order 1. So if it's much less than order 1, then there's not enough kinetic energy for the flow to the entirety of the flow to go over the topography. So you have flow blocking, and then in the 3D case, then you can have flow go laterally around the object. So this is called the flow around regime. So before moving on to the discussion of stratified wakes, I'd like to make one point that if there's an unstratified wake at these Reynolds numbers, so our Reynolds number here is moderately high, 20,000, then if it's an unstratified wake, so there's no density variation in the vertical, then actually you don't get any of these Lee vortices that I showed in the images towards the start of the talk. Instead of that, what you get is this indistinct patches of vorticity in this unstratified wake. And this is taken from, so this is a very similar geometry. This is a three-dimensional conical hill that they simulated using LES. So the conclusion is that you really need stratification for eddies of the type seen in geophysical wakes, or another possibility is that you have you consider a thin layer, right? For example, in the coastal ocean, where because of the fact that you're constrained in the vertical, you can have these quasi two-dimensional vortices spinning off the object. So the Froude number, which is basically the non-dimensional stratification, is defined as U0 by n times h. Recall that h is the height of the topography. And so this is a steady current. And here we have the streamlines the stream traces coming in here. So if the Froude number is small, so stratification is large, then what the flow wants to do is that, so most of the flow is blocked. And so what the flow does is go like so, go down, and then go slightly up, and then go down again in here. And you can see that and oh, by the way, I'm coloring so here we have the vertical velocity also in here, the colors. And so if I look at this Froude number of, sorry. So if I look at the Froude number of 0.86, so it's order 1, at this Froude number, you get these strong Lee waves in here. But for the very weak small Froude number with very strong stratification, you really get mostly a wake. Okay. So now let's look at the effect of the tide. So here the tidal excursion number, EXT, comes in, and the tidal excursion number, so the tidal excursion number is basically just the excursion length, UT by 2 pi FT, normalized by D. And as you can see, as is clear from this sketch, if the tidal excursion is sufficiently large, then you will get vortices of opposite sign in both sides of the object in here. Now let's superpose a current on this tide. So then you're introducing a current, a mean current, U sub C. And then if you look at, so now you're introducing this parameter R equal to UT by UC. And here what we see is that now there's a bias. So if R is greater or equal to 1, then essentially you're going to have, you would expect patches of vorticity on one side of the topography. But we'll see that that's not quite true. So before going into a more involved discussion, I want to give an overall view of what the flow looks like. So if I look at a plan view in here, so I'm plotting the vertical vorticity, the relative vertical vorticity, omega z normalized by f, the inertial frequency. Then you see the wake in here. But you also see this upstream. If you look at a vertical cut, you see the upstream block fluid, you see these transient Lee waves, and you see these kind of thin structures inside the wake in here. So here I'm plotting vorticity, and here it's velocity on the top. So what Pranav did was that he did like 2 series of simulations. So part 1 is where we vary the excursion number, the tidal excursion number, or the relative frequency, as I'll show in a moment. And here what we do is that we keep UT by UC, so the ratio R fixed at 1. So it's a pretty strong tide. And what we do is that we vary this tidal excursion number like so. And in part 2, what he does is that he varies R, and R is varied at a constant, so R is varied at a constant relative frequency. And so you get this line in here where so the parameter space is pretty large and LES is expensive. So we're not able to explore the entire parameter space. So part 1A, so that appeared recently in TRL. So I'll talk about how the tides affect vortex shedding. There's a question from Adele Monkpet, and the question is that, is the vortex stress changed with the non-constant stratification, with the pycnocline and with varying pycnocline depth? I think it would be, but in this case, we are looking at a submerged topography, right? So it's not like an island wake. So the stratification is more or less constant in the wake region. Okay.
There's one more question, Sutanu.
Oh, okay, let me see. Please explain the transient Lee waves. So the transient Lee waves. So if I can go back. Right. So let's say that I had a steady current. So if I have a steady current, what happens is that, and this is a low Froude number, then you have block fluid up to some certain height, and then you have an axis, and the entire tidal mass flux has to go through, right? And so you have an accelerated flow in the vicinity of the top of the hill. So that flow comes down, and there's stratification. And then it bounces, it goes down and up and so on. So that creates these, and you can see these isopycnal displacements in here. So that creates a Lee wave. So if it's a steady current, it's a steady Lee wave. But if the current goes back and forth like so, because of the tide, right, then these Lee waves are transient. So they form on one side, then they form on the other side, and so on. And then also depending on the parameters, for example, the steepness of the topography and this U0 by NH, the Froude number, these transient Lee waves may actually break near the topography and create strong local mixing. Let's see if there are any other questions. No. Okay, so as I said, oh, there's another question. Oh, not a question. Thanks, Nitendra. So let's see. So this is a large eddy simulation. So it's a non-hydrostatic model. And so we attempt to resolve most of the turbulence energetic scales, at least in the wake. The boundary turbulence is not resolved. So what we do there is we have our near wall model, and it's a pretty large simulation. But actually, these are expensive simulations, but not really big so much because of the number of grid points. I mean, for the non-oscillating problems, I mean, we can and also in the engineering problems that our group also does, we do much larger domains. But here the issue is that the tide is going back and forth. So if you want to have like a tidally average, cyclically average mean that converges, right, statistics, you need sufficient number of tidal oscillations. And let's see. And there's a conical obstacle, as I said, wrote here, h by d equal to 0.3. So it's relatively steep, and it's handled with an inverse boundary method. The Rossby number is 5.5, and Rossby number is the current velocity divided by f, the Coriolis frequency, and d. And then here you have the current, so it's a low weak rotation regime, high stratification, FRC is 0.15, moderate Reynolds number, and UT by UC, the velocity ratio of the tide to the current is 1. So in the absence of, Pranav has a very nice YouTube channel. And so let's see what happens. In the absence of tides, you see near wake, in the near wake, you see strong turbulence. And then at this scale, you don't really see the turbulence, but there is actually turbulence you see in the spectra in the wake. But really what jumps out at you is the von Karman streak, vortex streak. And there's a shedding frequency, and the shedding frequency is proportional to U by D, and that coefficient proportionality is the Struhal number. And the Struhal number in general is a function of body geometry, and it's a weak function of Reynolds number at high Reynolds number. So here we are at moderately high Reynolds number, and we find that the Struhal number is 0.26, which matches excellently with data, experimental data. So now I want to introduce this parameter relative frequency, which we find convenient to think about the problem using the relative frequency. So the excursion number, I said, is a ratio of length scales. The ratio of the excursion length scale to the diameter of the to sort of a characteristic horizontal length scale of the object. Now we can take a relative frequency f star, which is FSC, the current the shedding frequency, the vortex shedding frequency in a steady current relative to the tidal frequency. And the variation in the excursion number can be viewed as that in the relative frequency f star. So as we show here, f star is linearly related to EXT, the excursion number, and because the Struhal number is a constant around 0.26, and R is held constant 1. And so low f star means a relatively fast tide, FT, fast relative to the vortex shedding frequency. And low f star also means low EXT, because f star is proportional to EXT. So low f star also means relatively large lateral dimension of the topography. So what we do is we vary f star between 0.1 and 1. And so the excursion number varies in 0.06 and 0.6. So let's consider the case where f star is 5/6. So it's close to, they're close together, these two characteristic frequencies. So you can see these pretty dipoles forming in here during part of the cycle. So Z star equal to 0.02, 0.12, 0.24, 0.49. So it's the height above bottom normalized by the height of the topography. And you can see that the near body vortex pattern is quite different from what we see further away from the body. So as is written here, you have very high vorticity. So the vortex Rossby number can be up to 20 in near the body. There's possible, so let me not talk about this possible alignment. We are still looking into this. So the dipoles are unstable, and within a few diameters, they disintegrate, and you're left with the Kármán vortex. One interesting thing that we saw, and we were pretty surprised when we first saw it a year or so ago, well, almost 2 years now, is that the expected vortex shedding frequency is 5/6 ft, right? Because f star is 5/6. But the vortex shedding, or not the vortex shedding, the frequency of the vortices in the far wake occur at a frequency of ft/2, which is quite different. And the question is why? And just this is another plot that shows this period. So t equal to 13t, t equal to 15t. So you have these vortices repeating in here. 14t, 16t. You have these cyclonic vortices repeating here. Okay. So we show the same thing using spectra in here too, because what I showed previously was just an instantaneous picture. So statistically, what's going on, and the dominant peak in the spectrum of the lateral velocity v is, and this is shown in red in here, is ft/2, not ft and not fs sub c. And here you have this high frequency n in here. And so the span-wise velocity exhibits the strong peak at ft/2 in here, the subharmonic. So why do we have the synchronization of wake vortex frequency to tidal subharmonic? And we can look at it by looking at the spatio-temporal symmetries in the problem. So if you look at the Kármán vortex shedding, then what we have is that we have alternate shedding of vortices at every half cycle, right? So in other words, y being the lateral dimension, at ts/2, the entire vortex shedding cycle divided by 2, you have a vortex on two sides. So you have uxyt is equal to ux minus y t plus ts/2. On the other hand, the tidal forcing is imposing its own symmetry, because this tidal forcing can think of a body force on the problem that is space invariant. And so here the symmetry is that uxyt is equal to ux minus yt. So both sides of the center line of the object are the same. And also there's a repetition every tidal cycle. So now if we take this guy 2 and 1 and sort of match them up, then what we find is that nt must be equal to ts/2. Recall that t is the tidal period and ts is the vortex shedding period. And so it follows that the vortex shedding frequency divided by ft must be a subharmonic, so 1/2n. And so what we find is that when f star is equal to 5/6, then we find the first subharmonic. And then if we have like a faster, relatively faster tide, then fs becomes ft/4. So the fourth subharmonic. So here I wanted to show you that the wake vortex frequency, the frequency that you see in the far wake, and the vortex shedding frequency. So there are two different things in here. Let's play these movies. So this is a fast tide. This is a relatively slow tide. And you can see that a relatively fast tide, meaning fast relative to the vortex shedding time period, you have these pulses of vorticity, and these pulses of vorticity feed into the near wake, but they don't have sufficient time to grow as in the slower tide. Also, in the slower tide, what you find is that these vortex dipoles are formed. So the fluid actually, so for a steady current, right? So you have recirculating velocities in the lee of the obstacle. So now, if ut is equal to uc, then that low momentum fluid behind and adjacent to the obstacle is going to be pushed backward. And that's what you're seeing in this particular picture. So then you have basically vorticity of different sign being shed off from the same side of the object.
Sorry, what is UT by UC for these simulations?
Okay, so UT is the tidal velocity amplitude.
No, I was just asking what is the value. Sorry.
One.
Okay.
Yeah, but the thing though, Mani, is that even though R is 1, at all times the velocity is not in one direction because there's a wake, right?
Yeah, sure.
Right.
Thank you.
Sure, no problem. And then you can see this difference between the near wake and the far wake very more clearly if you do if you look at the time history of the vertical vorticity on a lateral transect. So here we have, let's say, our object. We have a lateral transect going, say, into the plane of the paper, and then I'm going to look at x star equal to 1, very close to the object, and x star equal to 4, further away from the object, the hill in this case. And if you see the small f star value, so that means a fast tide, then you have this very small tidal period, and that small tidal period is superposed on this nice larger scale wave. So this is a global instability. So you see this this vortex shedding mode very close to the body. And as you go far downstream, the only frequency that remains is that of T sub S. And T sub S by T is 4 in this case. So so it's basically 1/4 FSC, FFT. So FSC is 1/4 of FT, or T sub S is 4 times T. And similarly, you see that if you take f star equal to 5/6, now what happens is that your T sub S is equal to 2T. But clearly we see that there's a difference between the near wake and the far wake. And now if I put everything together, so this is like the summary of the tidal synchronization part, then what we find is that, so if there was a current, just a pure current, then you would have shedding at a constant Struhal number of 0.265. But the real Struhal number that you get is quite different. So depending on where you are in this parameter space, you can have so you have a tide that is faster than the current. But somewhat non-intuitively, the actual shedding frequency locks onto a subharmonic of the tide. So then what happens is that the vortex shedding frequency, the the wake vortex frequency that we see is smaller than both the tidal frequency as well as the natural vortex shedding frequency for a mean current. Okay, so
there is a question, Sutanu.
Oh, sure. Let me take a look at it. Why is there a lateral extension for E and F? Okay, which picture is that one?
Perhaps the previous slide.
This one?
I think yes.
E and F? Yes, yes. That's a great question. So what happens is that so remember I said that you have these dipoles that are forming, and so a dipole is a very unstable object. A dipole can actually shoot off in any direction because of the self-induced induction of the vortex path. And so you form these dipoles and they shoot off. They're of course interacting also with each other. So which is why you see a much larger lateral extension. Is that all right? Okay. So now let's take a look at form drag. So we found high drag states. So we found states in which the drag was much larger than for a steady current, and keeping the steady current the same value. And so this is impressed right now. And so here, what we are doing, part 1B, we are still looking at R equal to 1. So if you look at the form drag, how am I doing with respect to time? So I have so how many more minutes do I have?
Be around 18 minutes.
18 minutes, okay. All right, I'll try to take lesser time, so there's more time for questions if there are. So if you look at the form drag, so this is the dynamic pressure, PD. So this is the pressure that we actually solve for, which is the departure from the pressure gradient that causes the tide to go back and forth. And then because the tide is going back and forth, there is a background streamwise pressure gradient. And if you do the math, then that comes out like so. So this is the volume of the object times the acceleration of the bulk flow. The bulk flow meaning the background flow, sorry. And this, of course, integrates out to 0 over a tidal cycle, but that doesn't mean that it is negligible at any given phase. So we look at the mean value of drag. So mean value meaning cycle average drag. We also look at the phase average drag, and we also look at the deviation of the amplitude of the deviation of the drag from its mean drag, named RMS drag. So to look at the drag, of course, we have to look at the pressure. And so this is the upstream and this is the downstream. And right away, we see that as we go to F star equal to 5 over 6, remember that UT is the same in all of these, right? So the difference that we are saying is basically, and we related in the paper, is the difference between the spatial organization of the vorticity in the lead, the spatial as well as the temporal organization of vorticity. So as you go from a fast tide to a slow tide, you see a lot more of the low pressure regions behind the hill. And just to remind you that we had these 4 regimes, that if there's no tide, there's just a Kármán vortex street. And then if you have F star less than 1 over 4, then you have, if you have F star less than 1 over 4, you maintain this vortex sharing FSC, and then you've got FT over 4 and FT over 2. So this shows the phase average drag in here. So FD phase average. And if I look at F star equal to 2 over 15, so the fastest tide, then what happens is that since it's the highest frequency, of course, you see the largest RMS value of the largest excursion in the drag, in the amplitude of the drag. And because of that, you see for low F star, the largest RMS value of the drag. But then the mean drag is quite different. And the mean drag FD divided by, so this is a normalized mean drag. And the normalized mean drag changes from that of the current by almost a factor of 2. And the largest drag is in regime 4. And that, of course, has to do with the fact that you have these low pressure vortices behind the strong low pressure vortices behind the hill in regime 4. Now, if you look at the mean work done by the oscillatory form drag, and this is kind of has implications of parameterization, because the mean work is what is the energy that is removed from the flow, the tide plus current, and that is significantly larger than the mean drag multiplied by the mean velocity, UB. So in other words, there is a correlation between the drag and the UP that one has to take into account when we are looking at the energy loss of the flow to the bottom topography. And let's see. Okay, so this movie is not playing, looks like. But the point I wanted to make is that if you look at F star equal to 5 over 6, then you have you have these large low pressure vortices behind the body. But here you don't see that. Oh, this is actually. So we're looking at the dynamic pressure, and you see these small vortices in this fast tide, right? So you can't, it doesn't really, over the entire tidal cycle, you don't have a strong low pressure region behind the wake, behind the object. That is not the case when you have a slower tide. Now this low pressure vortex remains locked to the lee for almost the entire period, tidal period, which is of course why you have a stronger mean drag. Okay, so here I think one of the implications of this particular part is that if you have a continuous distribution of the topographic scales in the Abyssal Ocean, then there are obstacles with certain lateral dimensions, which correspond to, so let's say, F star between 1 over 4 and 1, and they can preferentially remove momentum from the background tidally modulated flow. So one has to take that into account in parameterization. So in the final 5 minutes or so, I'll talk about wake vortices and dissipation. And in here, so this will be more qualitative. So this has been submitted. And what I'll actually do is just go to the sort of the bottom lines in here. So if I look at wake vortices, so what we did here is we varied R all the way from 0 to 1, keeping the F star the ratio of the frequency is the same, 5/6. And what we find is that there is a gradual transition to this tidal synchronization as UT by UC goes from 0 to 0.2. And once you're around 0.2, so in 0.2, 0.25, and so on, then you have locked on to the tidal subharmonic. So it doesn't require really a very large tidal velocity and amplitude for this lock-on thing to occur. And why is this threshold 0.2? So we try to explain it using sort of looking at orders of magnitude of various terms in the momentum equation and so on. But I won't talk about that here. But mainly the thing is that if you have R equal to say 0.25 and larger, then what happens is that the tidal forcing term is sufficiently strong so that your recirculating fluid can be pushed upstream. And then once it goes upstream, then it interferes with, then it actually is quite effective in promoting the global instability mode. Now let's move to dissipation. So the turbulent dissipation, and what we find is that, so this is a turbulent dissipation, and this is the vertical vorticity. And so there's strong turbulent dissipation rate in the separating shear layers in here, and also in this recirculation zone. This is log epsilon star. Epsilon star is normalized dissipation. And if I look at a vertical cut, then you have dissipation associated with these transient internal waves that are being generated. But there's very strong dissipation in the lee of the body too. And the dissipation increases as R increases from 0.05 all the way to 1. So 0.05 to 1. And we try to actually look more closely at this feature in here. So this is the energy, this is a dissipation rate in the hydraulic response regime. So you have this accelerated flow above the topography, so that plunges down to this is a downslope jet, and then that kind of rebounds. Excuse me, my. Sorry, so I'd forgotten to keep my power on. So, and then what we find is that we have strong dissipation in these plunging and rebounding jets, and what we could come up with sort of scaling for the integrated dissipation in this particular region. So it basically scales as 1 plus the velocity ratio to the power 4, as you can see in this plot. Okay, so in conclusion for this particular part, as we changed R, we found that this tidal synchronization is observed even at weaker tidal velocities. And also we found hotspots of turbulent dissipation rate. And in future work, some of it is ongoing. We kind of, since we have these coherent structures associated with particular frequencies, we're doing a modal analysis of the wake using spectral POD. We're interested in looking at the influence of rotation on this multi-scale nature of the wake. And we're also interested in looking at the role of waves in wakes in terms of dissipation in the stratified bottom boundary layer. So with that, I'll end. I think I'm in time.
Yeah, perfect timing, Sutanu. Thank you. Do we have questions for Sutanu? You could either put it in the chat box. Yeah, there is a question from Jitendra. Will the tidal beams generation be influenced along the lee side?
Along the lee side by the wake?
I guess that's what he means.
By the wake. Yes. Yes.
Any other questions? So I had a question, Sutanu. You spoke about the drag towards the end. Can I think of the drag as a combination of the power put into the internal waves and the momentum put into these vortex dipoles? Or
yes, we could split that, right? Because but however you do it, right? So the pressure, it is basically the form drag is related to the actual pressure on the body, right? And part of it is due to the vortices that are basically impinging or generated at the body, and part of it is due to the internal wave variation, right? So it's kind of difficult to do a clean decomposition in here. But if I look at the momentum flux that's going out in this particular regime, Froude number of point, and for this kind of topography, strongly three-dimensional topography, the momentum that is being transported by the internal waves is not that large, really, compared to the momentum that's being lost by the wake.
Okay. But there could be some relation between the drag and the, let's say, the momentum in the far wake dipole.
Yes, but actually there's also turbulence involved, right? So
okay.
So yeah, you're right. You could do that. So you can do like a usual control volume analysis, right, across around the body, and some of the momentum is being lost because of internal waves, and some of it because of vortex dipoles. Yeah, you're right. You can absolutely do that, right? But that will be exactly the same as what we get by computing the form drag by taking the pressure. If our simulation is correct.
There are a couple of questions in the chat box.
Yes.
You want me to read them?
No, I can see them. Yeah. So the bottom boundary there, right? So what we did was that we essentially put a simple skin friction drag law. So instantaneously, we basically we related the velocity at the first grid point to the drag by a quadratic drag law. And we assumed unstratified there because it's true, it's the turbulence is mixing up the stratification right at the boundary. And yeah, so that's what we did here. That was Noni, right?
Yeah, and there's one more question.
You want me to deform and move mountains? Yeah, right. No, we didn't. We didn't put sediment in there. But you're right. I mean, I'm pretty sure that there would be erosion over a period of time. There's no doubt about that.
Yeah, she says that would be awesome. Okay, are there any other?
Yes, Thierry, you're absolutely right. And in fact, Cashion has mentioned this mechanism in the context of internal waves, right? So why are the slopes in the ocean close to near critical often, right? So there's a big patch of, if you look at the PDF, there is a pretty strong probability, better than a simple Poisson process probability, right? And that had to do with the fact that you have at critical slopes, you can have very strong turbulence, and then, so yeah. No, it's you're right, yeah, Thierry. But what we find, though, is, I didn't talk about it, is that the internal wave action in this particular 3D obstacle is kind of much weaker than what we have seen before in our 2D topography, because the flow really wants to, at this low Froude number, wants to go around the object.
Any other questions? Okay, if not, I would like to thank both Emily Schroer and Sutanu Sarkar, the two speakers of this session. Thank you very much. Both the talks were wonderful.